So, good morning everyone. My name is Fiona Reid. I'm a data scientist at Lloyds Banking Group. I was formerly based in Edinburgh, but I have absconded to the north of Scotland since the pandemic began, so I will now be working from the north of Scotland in the future. I worked at Lloyds for a little under 2 years, and prior to that I've got about 20 years of experience in various different industries like geophysics and in high-performance computing, working with large data sets. Today I'm going to talk about predicting risks using a combination of natural language processing and machine learning. At Lloyds I work with a small team of data scientists, and we basically work together to solve problems relating to risk in banking. So the outline of what I'm going to speak about this morning is basically to talk about the problem that we're trying to solve and sort of some of the objectives for what we wanted to do. Look a little at the methodology and how we've used NLP and machine learning to sort of try and predict risks in banking. Look at the modelling and the results from the modelling, and just sort of finish up with sort of some conclusions about sort of what we found and so on. So, the problem that we were trying to solve was basically that the risk oversight team at Lloyds Banking Group wanted to explore whether or not they could use data science to enhance their mitigation efforts for handling risks and issues. So they weren't previously using the data sort of in a data science type way. They weren't using the data, but not sort of using any sort of modelling and things sort of with it. We have a historical data set where we have a known outcome, and our objectives were basically as follows. We wanted to produce a prediction model that could provide insights into the likelihood of risks becoming issues in future. And because we've got the historical data set, we can basically build our model using the existing set of risks, work out which ones were actually issues because we know that answer, and then see how well our model does. We want to be able to run new risks through this model in order to obtain a risk score, so basically a probability of how likely a risk is to become an issue. And we want to basically gain improved comprehension of the sequence of risks which lead to issues, along with creating dashboard visualizations that let the analysts actually visualize what the model produces. Because most analysts do not care what a machine learning model produces, they want to be able to see how does that relate to the risks that I'm working with. The data itself is basically, it's historical, so we know what the outcome is, we know which risks became issues, we know which ones didn't. So it's what's known in machine learning as a supervised learning problem. We have a known right-hand side to what we're trying to solve. With two different data sets, one that consists of risks, some of which became issues, some of which didn't, and one that consists of issues, some of which were linked to the risks. Our first challenge when we looked at the data to begin with was basically that we had no direct one-to-one link between these two data sets, so there was no primary key to link them. So we actually had to work out which individual columns could be linked together in order to work out which risks became issues and which didn't. So once we'd done that, we basically then had essentially like an extra column of ones and zeros, essentially, or true false, of which risks were issues and which weren't. For actual data, we focused mostly on using the risk data in the modelling side of things, because if we want to predict new risks, there's no point using the issues data because we don't know whether that risk has become an issue or not yet, so we can only really feed in the actual risks that sort of get input. But the data is a mixture of both text and numerical data, and the text data is sort of further complicated in that it's both a categorical form and it's also a free-form text. So categorical text data is basically text data where you've got a series of known possible values. So an example would be if you had a medal won in the Olympics, you would basically have gold, silver, bronze, or none, and it has to take one of those values. Free-form text data is exactly what you think. It's basically text that somebody could have typed into Excel, they could have typed into a Word document. It can contain bullet points, all kinds of wacky formatting, and basically you have to clean all of that up before you can work with it. So most of what we'll do with the NLP examples that I'll show are referring to the free-form sort of text data, and that's basically because machine learning models need you to have the values that go into them as numbers. You can't just feed in a bunch of text. They can't work with that. You have to somehow convert your text to numbers, and it's not just by taking the ASCII code for the character and feeding that in. It's a little bit more complicated than that. So natural language processing is what we use to handle that free-form text data. It's basic natural language processing, or NLP, is a field of computer science. It uses computer-based methods to analyse text and speech. You're using it all the time, probably without thinking about it. Your predictive text on your phone is using it. When your email comes into your inbox, the spam filter is basically using NLP to work out sort of which emails you actually want to see and which ones you don't. Sometimes it doesn't get it right. You also use it in lots of communication technologies. So when you end up getting frustrated, connecting to a chat room, trying to get through to whatever company, a lot of that's using NLP to read the answers that you provide. Sometimes it is really just a case of, it gives you select from a list. Other times it is actually reading what you type in and trying to give you something sensible back, and usually resulting in lots of frustration. So it's not perfect. So some of the techniques that we actually use to work with the free-form text in our dataset were sort of described here. We basically used the NLP techniques to create lots of new features. So we started off with around 100 columns in our dataset, and we basically used lots of different techniques to create lots of additional columns that we could feed into our machine learning model. We did things like we counted the number of acronyms in the text, because the more acronyms that there are, the more complicated things might be. We counted things like numbers of words in the different sort of bits of text. So the text that we're looking at here is things like the description of the risk, the title of the risk, any comments that people have inserted relating to the risk. If there's sort of things to do with a project that relates to the risk, there may be things in there as well. So it's a whole bunch of different text columns within the data that we were sort of counting up word counts on, and also a big sort of combined column as well. We looked at things like the average word length. That may indicate how complicated something is, whether it's more risky or less risky. Character counts as well, fairly straightforward to just count them up. We looked at keyword counts, and we used them for both the risks and the issues data. So keyword counts, we basically took all the possible words across all the possible risks in the data, and we basically worked out what the most likely words, or sorry, what the most common words were within those sets of text. We got rid of the words like stop words, so is, the. We don't care about them. They don't really tell us anything about what's going on. And basically, we then put in essentially a bunch of extra columns for whatever the most commonly occurring words were. And the columns would contain the counts for each of those risks. We also did sentiment analysis, so how positive or negative a bit of text is. We did readability scoring, so basically looking at how complex the text is, so how readable it is. So basically a kid's primary one sort of textbook would be relatively uncomplex. A presidential speech would be pretty complicated in terms of the scoring. Again, that can also be indicative of how risky something might be, because if it's got lots of complicated sort of phrasing in there, it could be more risky than not, or vice versa. We looked at parts of speech counts as well, so that's basically how many nouns, verbs, adjectives, etc. we have in the data, and we also looked at something called topic modelling. I'll now run through a few of the different things that we actually looked at in a bit more detail with the NLP. So the first one I'll consider is sentiment analysis. So that's just looking at how positive and negative our text is. So I've got 4 sort of dummy documents here. For obvious reasons, I can't really use real data from the bank's systems here, but it kind of gives an idea of how it works. So I've basically got 4 documents. I've got the text of the document, and then I've got in the final column here, the overall one, basically how negative, positive, essentially the sentiment score for the text. So a score of around 0 is neutral, so that means it's kind of neither positive or negative. Less than 0 is negative, and greater than 0 is a positive sentiment sort of phrase. You can also handle negations, so if you compare document 2 and 3, you see that they differ by just the words not and very, and basically it's showing quite nicely that basically not very is coming out as minus a negative sentiment, and a nice sentence is coming out as a positive one. The actual algorithm that we use is something called Vader. It's one of the freely available Python libraries, so very, very easy to implement. And then I've included a little image that basically shows the sentiment scores as a histogram for one of our columns in the data, with and without the word risk included. And what you can see here is, with the word risk included, the sentiment is kind of roughly about -0.2, -0.25 overall. And if you remove the word risk, everything shifts over to the right, so it becomes less negative overall. So it's just to sort of highlight that actually just taking out the word risk from one of our text columns, because that word actually happened to appear in practically every single row in the data, everything kind of shifted over. So the overall effect, if you were actually just comparing these numbers, because the shape is kind of reasonably similar, it's not quite the same, but it's not far off it. It wouldn't matter whether risk was there or not, because it would all be relative, but it was just really to show what happens when you have or don't have sort of risk. Parts of speech tagging is another thing that you can do, so you can basically tag whether it's a verb, a noun, adjective, etc. Got a very simple sort of sentence here, basically showing how you can tag that particular word. And what we did for all of our individual text columns was basically to tag each word and then to count the number of occurrences of each type of word. So you're basically getting a column that contains the number of adjectives in that particular column of text, and so on and so on, and they're all adding extra features and extra information into your model. And again, that's a standard NLTK function that you can run whole pause tag. Other things that you also typically do in NLP is to vectorize the text. So it's also known as embedding, and it's basically the process of converting the text into a vector of numbers by counting what's known as the tokens, which are usually the words in the text. So I've tried to sort of illustrate it again with 3 very simple documents. So I've got 3 simple documents containing the text you can see here. If you actually count up the number of unique words that those 3 sort of little snippets contain, there's 11 unique words, and blue, bright, grass, green is it, sky, sun, the warm. And there's a method in Python that you can use basically to get Python to count up the number of times each of these words appears in the text. So basically what you end up getting is for each individual document you get a vector, which effectively equates to a sort of matrix if you've got lots of documents stacked on top of one another. And what you can see is for document 2, the word does appear twice, so you end up with 2 in the S column for that document. So here I've included all the stop words just for simplicity. Normally we take these things out, so things like is and that and everything would not normally be there. However, one thing the count vectorizer doesn't help us with is if words are very common in the text, it can overemphasize those. So there's actually something else that we can do instead. So it's the simplest way to vectorize text, but the words that occur frequently basically can end up being given more importance. So there's another method that we can use, and that's what we actually use with our data set, is what's known as TF-IDF, or term frequency, inverse document frequency. And what that is a statistical measure that evaluates how relevant a word is to a document inside a collection of documents. So it basically increases, the measure increases proportionally to the number of times the word appears in the document, but it's offset by the number of documents containing the word. So if every document contains, say, the word risk, it means that the emphasis of risk overall is not as high as it would have been. And you can see what happens here with the word is. So before we had 1, 2, and 1. Now we've got 0.36, 0.45, and 0.36. I haven't put the horrible maths that go into the calculation for this, and thankfully Python kind of does it for you. But basically now the word is in the second document is now much less sort of higher emphasis than it was if it was kind of vectorized. So we basically do this with all of our text columns and our sort of combined text columns. End up with a giant matrix. We also do things with the categorical text data. So I mentioned before that the categorical text data is things where you've basically got a set of unique values that the text can take. There's techniques in Python that you can use to translate a column that just contains text like that into basically a series of zeros and ones. So I've shown how you would do it with the medal 1. So here I've just got 3 examples. I've got bronze, gold, and none. Nobody got silver here. And basically what Python will do is you'll start off with the medal 1 column, and you'll then end up with gold, silver, bronze, and none. And they're populated with the appropriate values of 0 or 1, depending on what that particular person won, or in the case of the risks sort of data, what particular values sort of occurred within the data set. We also did this type of approach with how the risk, impact, and likelihood values changed over time. So you have residual and inherent risks, and basically if they change between low and low, low and high, low and medium, and so on, we basically encoded them first of all to have something where you had a unique set of values. So you would have essentially like 9 possible values, and then we translated it to one of these sort of 1-0 type tables so that you could look at the relationships between those as well. We took all of the features that we generated with the different NLP techniques and the big TF-IDF matrix and all the numeric features that we had in our data, and combined all of those sort of together into basically what goes into our machine learning model. We needed to remove a few words from our model because the risk oversight team felt that they were perhaps too predictive. And we basically started off with just under 100 columns in the input data, and the final data set ends up with about 40,000. So it ends up with a pretty big model. The actual modelling, we used a random forest and fairly typical training test split of 80 to 20. So 80% of our data was used for training, 20% used for testing. Some parameters of the model mentioned there. And I guess the key outputs that come out of the model are basically the probability of each risk becoming an issue. And also we can find out information about how important the individual features that went in were to the model. So when we were actually getting the outputs from the model, we had sort of discussions with our stakeholders, which are the risk oversight team, and wanted to find out, what did they really care about. So we asked them, did they want basically to be able to predict every risk, even if that included false positives, or did they want to predict every risk that only to predict the really most likely risks to become issues. And they wanted priority placed on the precision of the model. So basically, the model predictions were to be the most likely risks to become issues. And this is kind of a little cartoon to sort of illustrate what happens as you experiment with different thresholds within a model. So typically, if you basically increase precision in a machine learning model, the recall will sort of go down and vice versa. And we've got a little cartoon here that shows that the default threshold on the left-hand side is 0.5. So basically, in this example, we've got 7 false positives and 6 true positives. So that means that basically we were predicting more risks were not going to be issues that weren't than the actual true positive risks. But if we shift the threshold a little bit to the right-hand side so that we increase the precision slightly, basically what we're seeing is, okay, we've lost a couple of our actual risks, but we've now only got 1 false positive. So that means that if the analysts are looking at this afterwards, they can concentrate on the risks that are really problematic. So essentially they just take the most highest probability risks to become issues in terms of what they're going to work with. And they've actually got the ability in the dashboard to fiddle with these values and see what happens as they move the threshold, so we provided that for them. In terms of the actual dashboard, again, this is a sort of mock-up of the real one, because for obvious reasons, I'm not allowed to show the real one, but it gives a fairly nice idea of what we did. So basically, we used our risks and issue sort of data set, generate a model that can ingest new risks, and what you get out of it is effectively the probability of a risk becoming an issue. There's both a value and there's a bar, because it's easier for folks to view. It gives some information about each of the risks as well. And we also added some filters in there so that people could basically filter down by the value, the likelihoods. We also included things where you could filter down by business area, which was particularly crucial when lots of different people are working from different business areas. So somebody could select their business area and get just the risks that were associated with that business area. You could also then potentially drill down onto the values as well. We had multiple values here. Here I don't, just because I've only put a 20-line table in Excel to plot this. But this was a really, really nice thing for the analysts to be able to sort of work with. So, brief summary of what I presented. It's basically a case study showing how you can use natural language processing and ML to predict which risks are most likely to turn into issues in the future. You can use the model with new risks, so basically you can take risks that the model's never seen before and basically chuck them in. The key advantage of our model is that we're using both NLP and numeric features to basically get a better model than you would have potentially got if you just used the numeric stuff. Our model gets output through a dashboard which lets our stakeholders visualise the results, so they can look at what are the most likely risks to become issues in the future. They can drill down to their business area of interest, and they can apply various filters for whatever is appropriate to what they would like to look at. Yes, the key benefits are that it can improve the prioritisation of risks, because the model might actually pick up things that somebody didn't pick up, and it can potentially save time and money, because you can focus on the risks that might be more problematic than you expected to, or vice versa. And I guess it's just it's a nerdy data scientist. It's a cool way of using data to sort of help other people. Thank you.
Can I ask a question?
Yeah, sure.
What's the latency between the data, the documents, and the dashboard, I suppose?
We've basically got the actual model is sort of static in the sense that we're not continually ingesting new risks. If we get it in production, sort of at some point, then it would be possible to sort of run it each time. But somebody can potentially, we've provided the code in such a way that some of the analysts have the ability to just run it as a standalone on their desktop with the risks and just generate the data themselves.
Right.
So they can kind of run sort of as and when they want.
And they've got access to that data repository or the source documents?
Yeah, so the folks that work with the actual risks would have access to the data anyway, because that's, you know, they're the people that are actually entering the data and adding the new risks. So they have to have, I don't have access to it. I mean, I can read the stuff, but I can't write to it. They have, you know, the ability to access that.
From the dashboard, are they able to trace back to those source documents?
No, they would get it will display, so I guess on the cartoon one I haven't displayed sort of everything, but they would get something that would give them the ability to get back to it, so it won't link directly back into the data. That would be something that we would probably need permissions to do, but you will get at least the number that gives you the ability to go back and look at it. Which I guess if you've got access to both systems, then
yeah, you can do that.
What are the sources of all those risks then? Is it things like email correspondence? Is there any voice recognition stuff?
There's no voice recognition stuff in the stuff I'm working with. The risks themselves, I'm just going to scroll back so that I have my info on that one. The risks themselves are from basically lots of different areas of the business. So it's things like infrastructure, IT, legal, regulatory, resourcing, colleague, third-party supplier sort of stuff, all kinds of different things. So it's basically like a big system called the change management toolkit, which they've used in various sort of different financial organisations, and they all get inserted into there. And that's why we've got the ability to drill down with the different sort of business areas. So it's all kinds of different stuff, but it's all entered, I guess, as text. There's no stuff coming in sort of verbally from the data I'm working with. But I guess that probably does exist somewhere else in the bank. I just don't know.
I was saying that's had something to that. So we do a lot of work with utility companies and do exactly that, using machine learning to actually draw out keywords. And we also work with police and stuff like that. So,
it's quite interesting when you see what sort of keywords sort of come out. The things that you expect to come out, like the word issue, because if somebody mentions an issue in the text relating to a risk, that's possibly going to indicate that one is going to become a problem in future, because somebody might have written, this is similar to issue number, whatever. So you can get that sort of stuff is quite obvious, but you get lots of sort of common banking terms sort of come out as well, because it seems that if somebody's using the same terms, they seem to be the same things that go wrong.
And so in that kind of where language has different interpretations, is that something that you almost have to manually go back and correct, or can you?
You basically are using algorithms and just hoping that overall they do a good job. So I mean, the sentiment analysis does have some ability to sort of work with some of the semantics and things. So one of the sort of things that would be really cool to do with this type of model would be, rather than using the TF-IDF approach to basically vectorize your text, would actually we have a bespoke sort of language model for banking, which I'm not aware exists. It's sort of one of these sort of, we would really like this. Or have the ability to build it. But yeah, you basically, the sentiment model can take into account sort of the way that a sentence is phrased. A lot of the other things basically is to do with what specific words are there, rather than necessarily always the order of them and so on. So it's quite a tricky one. We also had lots of fun pre-processing the text at the beginning, because some analysts had done totally different formats from others. So we realised after a bit of time that we hadn't stripped off bullet points, and some folks had put bullet points in everywhere, and these kind of knackered up some of our algorithms. And it's only when it crashes and you realise, because you're not going to go through thousands and thousands of risks and look at the text for every single one of them to decide exactly what pre-processing to apply. So I've learned a lot about different ways of processing text before you can work with it. Okay.
What's the feedback been like from analysts in general?
they seem to be quite pleased with it. So yeah, it's saving them time, and the dashboard is kind of very intuitive for them to use. So they don't have to be data scientists to use it. So the analysts basically don't run the code. Other parts of the bank run the code. They just get access to the dashboard and kind of go click, 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 and they can sort of see, you know, what is predicted, which for them is great because they're not remotely interested in the sort of stuff I get up to, basically. Got 5 minutes to go. Morning.
So what you are doing in the data sciences, which are the use cases that you are actually leveraging in the bank, which you think that has shaped up during the past 18 months of pandemic?
I mean, I work in the sort of risk part of Lloyds, so most of the problems that I work with are sort of risk related, whether that's to do with sort of credit modelling sort of type stuff, or to do with basically looking at this type of problem where you're sort of trying to predict risks. It's, yeah, data science in Lloyds is far, far wider than what I do. There's lots of other parts of Lloyds that do that. I guess I only tend to sort of know about the sort of specifics of what our team work on.
So I have a follow-up question. In the legal space, so there are risks related to contracts that are signed by the organization.
Sure.
So what are you doing in that space, if you may enlighten us, please?
It's not something I currently sort of work on, so I couldn't really say.
That's all right. Thanks a lot.
No problem.
I hate to raise it. Do you use anything in terms of blockchain for sort of keeping these sort of analytical streams of information safe, secure, visible, or is it, how are you currently storing all of this data?
It's basically stored sort of on a secure server. I'm not personally using any blockchain technology. I don't know whether Lloyds uses that type of stuff or not.
Is that Google Data Studio one of those screenshots before?
Which one?
There was one where you're like charts and stuff.
Oh, this one.
Aye.
It's actually Power BI. So it's basically Power BI.
Yeah, it looks similar to these thing, yeah. 'Cause
Yeah,
I
no,
wanted Data Studio, so I wondered, yeah.
I had to find a way to basically mock up
Aye.
of the dashboard, and having never used things like Tableau,
Yeah.
I'd done a sort of very short course on Power BI and realised that it was really, really straightforward to just create something that looked kind of similar.
No, good.
And it's nice. I was really surprised how quickly I managed to get 20 lines of Excel to basically do this, where you could just click on a business area and go, there you go. And it's, yeah, very, very straightforward to do, but yeah, it's just Power BI. This one just ingests an Excel spreadsheet, but
Yeah.
the actual thing that we do.
And so yeah, I used to Data Studio quite a lot, it's quite fun. How quickly to do this.
Put that back to there.
I was waiting to see if any questions came
Okay,
through,
fine.
but nothing's come through, so.
Of course. Okay, thank you very much.
Thank you.
Laura, just to say, LinkedIn is very work. I run a cybersecurity cluster, but we also produce a cluster.
Okay.
So that we can use